we will continue the course that we had, the first lecture, and continue with the teaser. We have to understand the underlying models so that we can reason about those systems. So there are different kinds of models for distributed systems. The first model that we are going to look at is an asynchronous system model. Remember that a distributed system is a system where we have a set of nodes connected by a network, and this is the only way for nodes to communicate with each other is through message passing. In an asynchronous system, we cannot guarantee any bounds on the time to deliver a message. So, if a node sends a message and a receiver is expecting this message, it will take arbitrary time. We cannot have a guarantee on the time for delivery. Another issue is that we cannot also have any bounds on computing at a certain node, because the node might be overloaded or might have crashed. Basically, the internet is an asynchronous system. If you have a distributed application consisting of several nodes running over, communicating through the internet, we do not know a priori how long time a message will take from one node to another. We have some idea about how it normally takes, but there is no guarantee that it will be within this bound. We can say, okay, the message will take 100 milliseconds, but sometimes when the internet is overloaded or the server is overloaded, these bounds are violated. These take us to the issue of, can we implement consensus on a system that is geographically distributed over the internet? This turns out to be impossible. So consensus cannot be solved in an asynchronous system, even if a single node might crash. This, of course, has implications on a number of services that we would like to provide over the network. For example, if you want to provide an atomic broadcast service, an atomic commit service used in databases, or a leader election service, where we have a set of nodes, and one of the nodes will be a leader, so that it can coordinate the action of other nodes. So we have seen, or we just mentioned briefly, what was an asynchronous system. If you went to the other extreme, we can think of a distributed system as also a synchronous system. Where is a synchronous system appear? It appears quite often in embedded systems, where you have control over the system as a whole, over the computers in this system and the network. In synchronous systems, there are known bounds on time to deliver a message, and known bounds on the time to compute. In general, we also have the clocks of the different machines synchronized, so that there is always a known upper limit on the drift of the clocks on several machines. Essentially, if we have a controlled LAN or cluster environment, essentially it is synchronous. This is, of course, if we have control over the network within the cluster or the LAN. In synchronous systems, the consensus problem is solvable. And in fact, it is solvable with up to n-1 crashes, which means that if we have n nodes and even n-1 crashes, still consensus is solvable. And I think it's easy to understand why. So the intuition is easy. In a synchronous system, because we know the bound of how long it takes for a message to traverse a network, and also we know how long it takes to process a computation step in a node, then we can estimate how long time it would take to send a message to a node and get back the response. So this amounts to what we call accurate crash detection. And what's accurate crash detection? It's basically every node sends a message to every other node, and if no message from a node arrives within a bound, then we say that the node has crashed. And we can guarantee this because we have upper bound on message traversal and processing time. So definitely synchronous systems are useful, but they are not useful for application running over the internet. So how do we proceed? One observation we can make is that the internet, when everything is working fine, it is mostly synchronous. We have some idea about the upper bound of how long a message takes to traverse the network from a source to a destination. And occasionally these bounds are violated because of congestion, because of overload of a server, but most of the time things work fine. So one way to think about this system is to try to model them as systems where most of the time things work well, but sometimes things work bad. How to do that? We do this by a model that we call partially synchronous system. And in partially synchronous system, we think that the system is initially asynchronous. We have no idea about the time it takes for message to traverse or computing time, but eventually the system becomes synchronous. Now, in real services that we would like to build, what we want to say is that if we want to do something, for example, to run a consensus abstraction, we want to make sure that eventually we will have time to complete the initiation of the abstraction and the termination of the abstraction. Possibility of consensus. Actually, then, it turns out that consensus is solvable in partially synchronous systems with up, but not including half of the node crashing. And this is, of course, useful for internet applications. Another abstraction that we use when we try to build a distributed service is failure detectors. Failure detectors will be local components existing on each node that will give some opinion about if other nodes in the system are running or possibly have crashed. So let each node use a failure detector. The failure detector detects crashes. It could be implementing by heartbeats and waiting. And the failure detector might be initially wrong, but eventually, if we have a partially synchronous system, it will have correct decisions in the end. So a failure detector might not be accurate initially, but it will be at a certain point of time accurate enough for us to terminate the execution of our abstraction. So consensus and atomic broadcast both are solvable using failure detectors. In fact, they are solvable using a form of a failure detector that works on partially asynchronous system, which initially might not be accurate, might suspect failure of nodes, but eventually it will work correctly for the time to be able to perform the consensus or the broadcast and delivery of a message. How we're going to do that? Of course, just follow the course. And that will make you actually expert in building these types of abstraction. So I just mentioned failure, and possibly when we think about failure, we think about nodes crashing, but there are many other types of failure. So what types of failure are possible? Does node always crash? So we are going to study other types of failure different from just crash stop. So we are going to study Byzantine faults, where nodes can behave arbitrarily. It means send messages or omit messages and not adhering to the protocol or the algorithm underlying them. They can be sometimes malicious nodes, or the software running on these nodes are actually faulty. We are going also to study self-stabilizing algorithms that I'm going to describe shortly. So, what is Byzantine faults? Nodes might behave arbitrarily. They can send wrong information or they can omit message sending. We will see that Byzantine algorithms tolerate faults, such that if we can tolerate up to, but not including, 1/3 of the nodes, we can still perform critical algorithms and services like consensus and atomic broadcast. Normally, non-Byzantine algorithms tolerate only up to half of the machine failing, but not including, of course. Another class of algorithms are self-stabilizing algorithms. These are algorithms that are running forever, but sometimes, temporarily, they behave badly, but they always converge to a good behavior. So these are robust algorithms that run forever. The system might be temporarily incorrect, but eventually always become correct. One way to think about these systems is that we can say that if we look to the whole space of possible states the system can exist in, part of these possible spaces we call legitimate state. So legitimate state, and that is this part. And the system as a whole can exist either in this subspace, which is legitimate state, or here, which we call an illegitimate state. So a self-stabilizing algorithm has two properties. We can say an algorithm is self-stabilizing if it has a convergence property, which means if the system as a whole starts from an illegitimate state, this is an illegitimate state, so legitimate state, then the system eventually moves to a legitimate state. The other property of a self-stabilizing algorithm is a so-called closure property, which says if you are in a legitimate state, you will continue be in a legitimate state. So what are self-stabilizing algorithms good for? They are algorithms that are used to, especially in networks, to handle transient failures. A system that gets into a bad state, but the system by itself reverts to a good state. They do not need initialization, and we will see in this course that we can actually compose easily self-stabilizing algorithms to build bigger and bigger services. Here's an example of a self-stabilizing algorithm. This is the first self-stabilizing algorithm was proposed by Dijkstra a long time ago, and it's called the token ring algorithm. In the token ring algorithm, we wish to have one token at all times circulating among nodes. But this system sometimes create multiple tokens. So a self-stabilizing algorithm, in this case, will be able to self-stabilize, which means move to a state when there is only one token, even if we start with 0 tokens, 2 tokens, or 3 tokens. So eventually it will ensure there's only one token running in the system. So what is the future of distributed systems? Many of the algorithms that we are going to study work only assuming few number of nodes knowing each other. But currently, we have systems with hundreds of thousands of nodes or even millions of nodes. And these we call large-scale distributed systems. So we are going to study some of these algorithms related to large-scale systems. Systems are also dynamic. So some of the algorithms assume a fixed number of nodes, and it works only with this assumption. But many systems, and actually all practical systems, are dynamic systems in the sense that nodes can crash, new nodes can join, a node can be taken off for maintenance and rejoining again, and we call these systems dynamic systems. We are going to study some of the algorithms related to how to reconfigure systems that are dynamically evolving. Examples of large-scale systems are peer-to-peer systems and cloud computing. Examples of peer-to-peer, you can see Skype, BitTorrent, and PPLive. PPLive is a system for media distribution. There are many other systems. And peer-to-peer systems are a system consisting of nodes on the edge of the network that cooperate together. Cloud computing is based on data centers where you store, where you have hundreds of thousands of nodes, and these are used to provide different services to large number of users. Think of Facebook, Gmail, etc. In summary, distributed systems are everywhere, and distributed system is a set of nodes cooperating over a network. They can only interact through message passing. There is a number of recurring core problems. We can call them also services or basic building blocks when we want to build fault-tolerant distributed systems. These are consensus, different types of broadcast, electing a leader to coordinate action of a set of nodes, creating a view of a shared store, and other things too. There are different failure scenarios in regard to both the network and processes or nodes. Nodes can crash and stop working. We can behave in an arbitrary way that is Byzantine. And we can have also algorithms for systems that temporarily are disturbed or perturbed and later can fix itself. These are called self-stabilizing algorithms. So the area of large-scale dynamic distributed system is an exciting area with a lot of challenges. So let us start the course.